Welcome to our Semiconductor education program. I'm Vincent Chang. In this lecture, I'm going to teach you a very simple but important concept in analog amplifiers. It's called the concept of voltage buffer. Let's consider a case to transmit a signal from left to the right, from source side to the load side. On the source side, there are two components: the voltage source Vs and the series resistance, the internal resistance Rs. On the load side, it's very simple, a load resistance of RL. So now we are going to transmit the signal from left to the right. So the simplest way of doing this is use the direct transmission. From the point A to point B, just direct transmission, a direct transmission line. So in this direct transmission case, so what's the relationship between VO and Vs? Based on the voltage dividing rule, it's very easy to get the relationship between VO and Vs. So VO equals Vs times multiply a dividing factor, which is the RL divided by the total series resistance of the network. So, what's the issue? Let's consider a worst case scenario. A high internal resistance, but very low load resistance. So when the source resistance is high, but the load resistance is low, then what happens? Then you have very large denominator, but very low, very small numerator. So if the Rs is greater than RL, then VO will be much less than Vs. What does that mean? It means during the transmission, a large portion of the signal is lost during the transmission. So the second way of doing this is to introduce a voltage buffer. So let's plug in a voltage buffer between point A and the point B, the orange block. So the Ri stands for the input resistance of the buffer. The Ro stands for the output resistance of the buffer. So there is a voltage control voltage source on the output side. So with the controlling the transfer ratio, the voltage transfer ratio of Mi Vi. So three components: Ri, Mi Vi, and the output resistance Ro. So let's first derive the relationship between VO and the Vs. So two voltage dividers. So on the left hand side is the divider between Vi and the Vs. So on the right hand side is the divider between Ro and the RL. So VO equals Mi Vi times the dividing factor RL divided by Ro in series with RL. So combining these two equations, you get the result. So VO, so just look at the left-hand side, equals mu Vs times multiply 2 dividing factor, one on the left, the other one on the right. So let's consider a scenario. If we can design a buffer with a very high input impedance, very high input resistance. Let's say in ideal case, we have the infinite input resistance. Ri approaches infinity. And then Ro is zero output resistance. Then what happened? Then the two dividing factor on the left-hand side equals what? 1, right? So VO equals mi Vs. So if mi is greater than 1, then the circuit becomes an ideal voltage amplifier. So what's the characteristic of the ideal voltage amplifier? Infinite input resistance, 0 output resistance, and mi is greater than 1. But if mi equals 1, then what happened? VO will be equal to Vs. So this means during the transmission with the ideal unity gain buffer, then no signal will be lost during the transmission. Summary. So in the worst case scenario, if we use the direct transmission from left to the right, from point A to point B, with large signal resistance, a very low load resistance, and a large portion of the signal will be lost during the transmission. VO will be much less than Vs. But if we plug in connecting a unity gain buffer between point A and point B, then VO will be exactly the same as Vs. So let me ask you, so what's the three characteristics of the ideal unity gain buffer? 3. So you may want to just take note. The first one is what? Infinite input resistance. And what about the second one? 0 output resistance. And mi, the voltage transfer ratio, equals 1. So I hope you gain the fundamental concept of the voltage buffer. Thanks for watching.